Purushottam Chakraborty from the Saha Institute of Nuclear Physics in India. And the title of presentation is Metal Quantum Dots in Glasses for Nanophotonics. So we're back to nanophotonics and to quantum dots. Welcome, Professor Chakraborty.
Okay.
Am I audible?
Yeah.
Okay, you're online. We hear you and we see you.
Okay, good. Thank you very much. Let me first of all thank the organizers for giving me the opportunity of expressing some of my views, and let me thank the chairman for chairing the session. I'll be talking on the metal quantum dots in glasses for nanophotonics. What I'm going to do actually, we are synthesizing metal quantum dots in glasses. And I would tell you how these metal quantum dot glass composites can be an excellent material as a nonlinear optical material for the photonic applications. Michael Faraday proposed in 1857 that microscopic particles of silver and gold are responsible for the beautiful coloration of the ruby gold decorative glasses. The suspensions of nanometer-sized particles were first employed to impart decorative colors. Particle size distributions in these suspensions can be controlled.
Excuse me.
Yes,
excuse me.
yes.
You're not sharing your presentation, so you have to share your screen.
Oh, I see.
So we cannot see it.
I see. I'm sharing, not sharing.
We cannot see your screen yet.
Just let me see. Why not? Okay, sharing. Okay.
Sharing screen, and then we will see your screen and still hear you.
Okay. Now, is it now? Has it come now?
Yes,
it's now.
Has it come now?
Now go full screen, please. Go full screen.
Yeah, is it okay now?
Yes,
correct.
Perfect.
Okay.
Yeah.
Okay.
Yeah.
I'm going to talk about the fabrication of the metal quantum dots in glasses for nonlinear optical applications and for photonic applications. As I mentioned already, which you couldn't see that, Michael Faraday was the first. He proposed that microscopic particles of silver and gold are responsible for the beautiful coloration of ruby gold decorative glasses. And the particle size distributions in these suspensions can be controlled across the visible spectrum by thermal annealing. You see, the decorative glasses, that is just because of, that is in a church of Notre Dame in Paris. All the colors are coming because of the metal quantum dots in the glasses. Okay, this is very pedagogical, but just see, in a quantum dot, the electron is confined, and electron, when it is confined in a quantum confined structure, the energy of the electron is quantized, and it is n square h square by 8m L square. And just by changing the expression, we can get the E1 is h cross square pi square by 2m L square, where L is the dimension of the length in one-dimensional quantum structure, and this is the energy in the first quantum state. That means n is equal to 1. As you can see, this is contradictory to the classical system, because in classical system you can make the particle motionless and you can get the energy 0. But in the quantum system, if the particle energy cannot be 0, you have some finite energy even at the first quantum number. Anyway, and I'm just recapitulating in just 1 or 2 minutes that if you have an atom and if it is exposed by the electric field, then if it is strong electric field, then naturally the electron cloud and the nucleus, the positive nucleus, they get separated, and of course, then you are creating a dipole moment, and the polarization is proportional to the electric field. And that means polarization is equal to some constant multiplied by the electric field. And that constant is basically containing an atomic polarizability, or the polarizability alpha, and the dielectric constant. Now, if you talk about a number of particles, number of atoms, innumerable number of atoms in a system, then if it is exposed by the electric field, and of course, every individual atom is polarized, and therefore the polarization is epsilon 0 n alpha E. So n alpha, you can call it as a first order susceptibility, and epsilon 0 is once again the dielectric constant. So it means the polarization is basically is proportional to the linear susceptibility. That's all about the linear optics, but I'm going to talk about the nonlinear optics now. So it is a linear optics means electric field was not enough to give you the higher orders of the susceptibilities. Therefore, if you make a plot of the polarization as a function of the optical electric field, it is just the linear function. And of course, and we can get the refractive index is basically coming from the equation 1 plus chi1 square root of that. Now, for the symmetric structure, the polarization as a function of E is a symmetric structure in a straight line, but for a symmetric structure, it could be also for the nonlinear effect, it could be symmetric. You see the curve one is for the nonlinear one. Now, polarization is, of course, the chi2 comes in for the higher optical fields, and chi3 and chi4, chi5, and so on. I would be talking basically on the chi3 part, because I'm talking about the photonics, I'm talking about the glasses, I'm talking about the metal quantum dots which are embedded in the glasses. Now, when the driving optical field is much smaller compared to the intraatomic field, you are getting the linear part of polarization. And when the driving optical field is extremely high compared to the intraatomic field, or at least comparable, then you are getting the nonlinear polarization. Okay, and the second term gives you the cos 2 omega t. So 2 omega t means you are generating the 2 photons. So 2 photon generation or the 2 photon absorption comes in the second term of the second part of polarization. And similarly, if we just again expand the expression, then chi3 E 0 sine omega t cube, it comes about 1/4 chi3. Chi3 is the third order susceptibility, E03 cos 3 omega t. So it is the third order harmonic generation. The frequency is triple, and it is called the optical card effect. And the total refractive index is n0 plus n2i, where n0 is the linear part of refractive index, and n2 is the nonlinear part of refractive index multiplied by the intensity of light. Now, so I have to skip many things. And then first of all, we have seen when you are implanting metal particles in the glasses, this is absolutely, you are getting any enormous amount of metal particles. You can embed innumerable millions of metal particles in the glasses, which you cannot fabricate by chemical doping or by chemical process. Okay, so metal glass composites made by ion implantation have much higher local concentrations than compared to the melt glass fabrication process. And such metal composites exhibit significant amount of nonlinear optical response, that is the chi3, in picosecond to femtosecond time domain. I will quickly go. There are some materials like lithium niobate, barium, sodium, niobium oxide, cadmium, okay, germanium, etc., etc. These are, of course, materials for giving you the electro-optic switching properties or electro-optic properties. So these are not good for nonlinear. These are not very good for the photonic applications. These are very good for electro-optic or optoelectronic applications. Now, chi3, we are talking about the chi3, which is basically we want to have extremely high chi3 in the femtosecond or in the picosecond time domain, because our idea is to get the optical computation. Our idea is to get the optical switching. So the switching, we need extremely small time. So the optical responses or the third order optical responses have to be generated within the extreme small time domain. So glasses are beautiful optical isotropic materials. They are centrosymmetric. This is the main idea. So the material has to be centrosymmetric. So glass is extremely centrosymmetric, and glass is amorphous. Now, if you just compare with glass in crystal like silicon dioxide, you can see basically they are the same materials composition wise. They're the same materials, but glass has more open structure because glass is having supercooling. If you talk about starting from the liquid of silicon dioxide, and if you allow to it's super cool, it becomes a glass, and if you do quenching, then it becomes a crystal. So basically you are having a crystalline structure of the same material, or you are having a glassy structure. In the glassy structure you have more open structure, so that you are able to accommodate more and more metallic particles in the glasses. Now this is the first thing. And secondly, glass we are using because it's giving a high amount of figure of merit. So figure of merit is defined as delta n, that is the change of the refractive index, divided by tau multiplied by epsilon 0. This is the linear part of the linear the extinction coefficient or absorption coefficient, and tau is the relaxation or response time of nonlinearity. So for the glasses, this tau is smaller and alpha 0 is also very small. So for the glasses, we are having very high figure of merit. Now, as you take an example of materials like quantum wells, like gallium arsenide, gallium aluminum arsenide, gallium arsenide, quantum well structure, then the figure of merit is 10 to the 2, 10 square. The polydiacetylenes, it is some kind of material which is also giving you the nonlinear optical responses, but figure of merit is even much more higher, 10 to the 4. But if you talk about glasses like lead glass or the titanium glass, then it can have the figure of merit 10 to the power 6. So which is extremely good enough for getting nonlinear optical responses or for the photonic applications. Now, n equal to, as I mentioned, n equal to n naught plus n2i, where n2 is the nonlinear optical refractive index, which is equal, which is a function of the third order susceptibility. So it is basically giving you, so it is a function of real part of chi3, because chi3 is basically having two components. One is a real part, one is an imaginary part. And similarly, you have also the absorption coefficient beta. So beta also equally, it is also related to the imaginary part of the chi3. So the detailed expressions are, so if you have a strong linear absorption provides a coupling between the real part and the beta or the imaginary part of chi3 and n2, then of course your expressions are modified. Now, this is the main thing we are applying. See, this is the classical confinement where the metal particles are extremely small compared to the wavelength of light, which is incident on the metal particles. Then the electric field that is acting and polarizing in the free charges of these clusters can be very, very different from the macroscopic field outside the clusters. These metal valence electrons move freely inside the clusters, which is forming a strong dipole in applied electric field, enhancing the local field inside the clusters. That means the local field inside the clusters is very much different compared to the macroscopic field, what is actually occurring in the entire medium. I'm talking about a medium which is a host like the glasses, and I'm talking about the metal particles, they are suspended in the glasses. Now the question, how many particles you can accommodate? That is very important. Okay, and what is the role of oxygen there? That is, of course, there are very much detailed things. Time is very short, so I have to go quickly. And so you see the local field in the cluster is inert. So macroscopic field in the medium times a factor which is called the local field factor. Okay, so this is very important. Therefore, now another is the quantum confinement. That was the dielectric confinement, because that was the classical confinement. In that case, nanocluster size was much, much smaller than the wavelength of light. And this is, again, the metal nanocluster size is very, very small compared to the delocalization lengths or the mean free path of the conduction band electrons. So that gives rise to the decomposition of the bulk conduction bands and the valence electrons into a set of discrete energy states. And you know already that energy is this. So drastically, these two things, this is modifying the quantum states of the electrons and their interaction behavior with applied optical field. These two, the dielectric confinement and the quantum confinement, these two in combination giving rise the photonic behavior of the metal particles in the glasses. This is the absorption coefficient or the extinction coefficient, what we have calculated applying the Meek theory of electromagnetic radiation interacting with the metal particles in some host material. Then extinction coefficient is 6 pi, etc., etc., where n is the number density of the metal particles, b is the volume of each particle, nd is a refractive index of the host here in the glass, lambda is the wavelength of the incident light, and A nu and P nu are the partial wave contributions of the scattered wave to the scattered wave by electric and magnetic monopoles. Now, when the size of the particle is comparable to the wavelength of light, I mean, if the size is very, very small, the size is about 100 nanometer size, maximum 100 angstroms, 10 nanometer, then we have seen that the expression that the monopole, the magnetic monopoles, magnetic multipoles and electric multipoles, they are basically, that can be ignored, and then you are getting a very simplistic expression for the extinction coefficient. This is 18 pi p nd cube, etc., etc., where you can see this epsilon m single prime and double prime, they are the two, this is the real part of is the dielectric constant of the metal particle, and epsilon m double prime is the imaginary part of the metal quantum particle in the glasses, and nd is of course the refractive index of the host. Therefore you can see, so basically as you can see, k becomes maximum, k can be maximized by minimizing the denominator. So this means this has to be 0, this has to be 0. That means epsilon m the single prime equal to minus 2nd square, isn't it? So it means, so the resonance, you can have a resonance, you can have the optical resonance. This is the surface plasmon resonance, and we have calculated of the metal particles of different radii, that metal particles, they are having surface plasmon resonance at different lambda of the optical wavelength. But when the size of the metal particle is about 10 nanometer or even less, then the position of the peak doesn't change. Okay, I have to quickly go. This is coming from the Meek expression, Meek theory, of course. And this is, of course, and that SPR, as I mentioned to you, this is the SPR frequency, because the light wave frequency of the conduction band electrons, the conduction band, they are collectively oscillating and are creating plasmons, and those plasmon frequency has to match with the frequency of the optical frequency, optical light. Then you have the SPR band. Okay, and this is the signature that you are creating metal particles in the glassy materials. Now, this is as you can see, this is the plasmons. They're the collective oscillations of the conduction electrons at the interface between metal and dielectric. So surface plasmon resonance is the resonant oscillation of conduction electrons at the interface between a negative and the positive permittivity material, which is stimulated by the incident light. Anyway, this is the experimental system. So there are many, many beam lines. I have used one single beam line for ion implantation. We are implanting ions at different energies, and we are controlling by ion implantation the distribution of the metal particles and in the glasses. These are the metal particles. This is the transmission microscopy of the microstructures of the tin dope. This is the tin implanted silica glasses. As you can see,
we have to come to the last slide now.
Okay, thank you. These are the structure, and you can see these are the different kind of metal nanoparticles. This is for the cobalt one. Now I would quickly go that we are really getting the nonlinear optical responses of these by using by a new device, new technique which we have devised, which is called the anti-resonant interferometric nonlinear spectroscopy. This is a very new kind of experimental setup which we have developed in our laboratory, and by this technique we are measuring the ARINS signal, and that signal is giving a nonlinear phenomenon. As you can see, that the nonlinearity in the ARINS signal as a function of incident intensity, that gives you the signature that you are nonlinear diffractive index. Now we have actually, I will not go into the details, but I will take only one slide to show you.
No, you go to the last, please.
Okay, okay, thank you. And so this is, we also used the Z-scan technique, and for the Z-scan, you know that the sample is moved across the focal point, and then you are getting the different, cutting the different intensity of the light, and you are getting, you see, we are getting the peaks and valleys of the things, which is measuring. Ultimately, we are measuring the.
Thank you very much for the presentation.
Okay.
Thank you.
This is the table. This is the table which is giving you the values of the refractive index, nonlinear and imaginary part of the Chi3, what we have measured for the different materials in the glasses. Thank you very much.